So you're seeing a pattern here. We started off just doing sums of forces, net force, figuring out sum of forces, figuring out net force. Not caring about its motion, not caring about mass acceleration, not caring about the fact that F net equals ma, because we started off just finding F net. You know what's coming, right? So then we take all that and we make it equal ma, and it gets a little bit more complicated because now we're concerned with the acceleration and the mass. So what happens next? Well, we've spent lots of time figuring out, frictional forces and normal forces. Whoops. Well, that's wrong. And normal forces and applied forces. But we've been doing that pretty much irregardless of, regardless, thank you, sorry. I am dopey today. Regardless of what that means for the acceleration of the object. So guess what we're going to do now? Plus all our mu s or k stuff. Okay, so now we're going to throw all that together. 4D is fairly challenging usually, but we're going to walk through it together and you'll be just fine. You now have 3 equations for every problem because you've got sum of forces x, sum of forces y, and mu equation. So that gives you lots of pieces to figure out how to find the missing puzzle pieces. So we're going to go ahead and do 4D. This is on 146, and we'll just walk through it together. Student moves a box of books by attaching a rope to the box and pulling with a force of 90 newtons at an angle of 30 degrees. As shown, we can draw that for ourselves. The box of books has a mass of 20 kilograms. Coefficient of friction between the box and the sidewalk is 0.5. Find the acceleration of the box. So let's draw our free body diagram. 30 degrees, force applied, 90.0 newtons, and we have Fn, Fg, force of kinetic friction. So I'm going to go ahead and break out my applied force. See where all those endless calculations you did for friction with ropes will help you? The reason I make you calculate that, 12 times? Okay, so we want to know the acceleration of the box. Well, what equations do we have to work with here? We have sum of forces on the x, we have sum of forces on the y, and we have mu k equals Fk over Fn. Where's our acceleration going to occur, on which axis? Assuming that there's no Jedi force involved here. X-axis. So this is, I'm going to note that this is where I'm expecting my acceleration. That's going to help me because I'm going to end up using that axis. Oh, yeah, that's the y that I wrote that on. I said x and I wrote y. There, sorry. Thank you for the crinkly eyebrows. Oy. Okay. So, what do we have on the x-axis? Force applied x and Fk. And I'm not going to get to the MA just yet. What do I have on the y-axis? Fn plus F applied y, because it's upward, minus Fg. Fortunately, that's all on one axis, so that's not so terrible. I should move some of these up. And the mu k in this case is probably going to be something that I use to create an expression that I can substitute back in. Now, let's add one more thing here. Sum of forces on the x is also equal to mass times acceleration. So therefore, f applied x minus fk equals ma, and the a is what I'm going for. That's what I need to find. So, you know, easy peasy. I just need to find force applied x and fk. How hard could that be? Actually, boy, this one is... Oh, yeah, okay, I see the trick. So, let's see if we can create an expression for fk. So we got mu k fn equals fk. Hey, cool. Excellent. Do I need to do something else? Well, we know that this equals 0, so fn plus f applied y minus fg equals 0. Can I get an expression for fn out of that? Yeah. So I can do fn equals fg minus f applied y. So I went from creating an expression. Oh, I should have gone the last step here, divided by mass. I went from creating an expression for the thing that I'm solving for to finding the pieces that I'm going to plug into that. So when I was here, I know that I have that. I know that I have that. Well, I need this. Well, the only way to get this is to do something with the mu k expression, because that's an easy way to create an expression for fk. Okay, well, I have this. Oh, I don't have this. Well, the way to create an expression for that is to go back to the y-axis and create an expression for my sum of forces on the y. So in these problems, you tend to use all three equations and do multiple substitutions. So let's see what this actually looks like if we sub everything in. I'm going to work backwards from my last substitution. So this is going to go in there. So I have then mu k times fg minus f applied y equals fk. Okay. So now I have an expression for fk. All right, I can take that and stick it into f applied x minus mu k fg f applied y equals fk. Cool. So now I can take this and sub it into the... Wait, did I skip a step? Oh, good heavens, Moser. Yeah, I screwed up. Okay, sorry. Equals A, and that whole thing is divided. I went to the next substitution and forgot that I was there. I do feel especially stupid today. I'm sorry. Okay, so we created this expression for fk, which we subbed into there. Good so far? It's a little ugly. I'm going to admit that right off. So let's go through and see what else we need to do here. So f applied x is equal to f applied cosine theta minus quantity, this is mu k, times, and I'm doing double brackets. You could distribute that mu k. I've chosen not to yet. We will in the end, obviously. mg, oops, minus, well, f applied y would be f applied sine theta, close brackets, whole bloody mess divided by m equals a. That's not so bad. Now, a word about substitutions versus solving for each and every step and plugging your numbers back in. You can do it both ways. There will come points where you're missing a substantial number of factors and you have to rely on the algebra, and you have to create expressions out of which you can factor and cancel things. So it's a good habit to get into. You know, in essence, you can solve for those little nested pieces and make a list on the side for yourself. And I've done that when it's especially ugly because there's nothing worse than having written down none of those intermediate values and then screwing something up in your calculations. So I do tend to do that. Let's plug in some numbers and see where we're at. So we've got 90 cosine 30 minus quantity 0.5 times, quantity, how do you say that? Quantity of 20 times 9.8 minus 90 newtons sine 30, close parentheses, close brackets, all divided by 20 kilograms. Hoi. Did you get a number like that? Good. On these, the further you get into the sort of nesting expressions, the harder it is to tell what your signs should be. So be really careful in the early part of this with signs, positive and negative, because of course it matters a tremendous deal if you're adding or subtracting forces. If they're in the same direction or not, it'll change the magnitude of your answer. So final answer with sig figs, 0.12 meters per second squared, and I can't remember what direction they were pulling the box in direction of pull. You know, because it is a vector, so we need to know what direction. And like I said, I forgot if it was left or right. Makes a rope, pulling, yeah, it doesn't say. So, okay. Isn't this fun? It's okay, you'll all survive. So get started on the book work and do all the book ones. I will copy the worksheet, and it's another one that's going to be all